this demonstration, I'm going to use Le Chatelier's principle to help me predict the changes in voltage in this voltaic or galvanic cell. Right here I have a Daniell cell, classic Daniell cell. I've got my zinc electrode, my copper electrode, I have my oxidation half cell, I've got my reduction half cell. We know electrons are going to be pushed out from the anode and pulled back in. We go from anode, that gets pushed through the voltmeter, okay, to the cathode, all right? And right now I've got a voltage of positive 0.72. Now that's volts, and this is telling me that this reaction is spontaneously going. Positive volts tell us that we have a preferred pathway in the forward direction. Notice I have a salt bridge here that is providing me that, helping me provide electrical neutrality so that electrons can flow. Now, what I'm going to do is I am going to add water to this half cell. And let me see if I can predict through Le Chatelier's principle what would happen. Okay, first and foremost, Le Chatelier's principle clearly states that if I have a reaction that's reversible, okay, it's not too spontaneous, if I add a stress to it, that reaction is going to change one of the directions spontaneity, meaning it might go forward better or the reverse better. In the case of a battery, we kind of want that to go forward. Going in reverse is not something we normally want to do, but I want to show you that. So before we do so, I want to talk about the standard potentials. This is the oxidation potential, 0.76. This is the copper's, or copper plus 2's standard reduction potential. Remember, I changed the sign for the one that oxidizes, the species. I add them together, I should get a net potential of 1.10 volts. Now, if you notice, my Daniell cell is 0.72. Now, why would that be? Why am I lower than what the tables tell me? Well, because the tables are based on a set of conditions. Aha! If I change the conditions through Le Chatelier's principle, I can change the voltage. You can play like you're some master of the universe here if you understand Le Chatelier's principle. We want to gain much understanding through this. So, understanding that this is telling me something about how well this reaction is going forward, and I have the overall here. All right, so before I try to improve this, I'm going to try to make this battery not go as well in the forward. So I'm going to pour water into this reduction half cell first. Now, what's the consequence? Well, think about your reactants and products. I have copper plus 2 that's being reduced. I have zinc being oxidized. I'm separating the reactants by 2 half cells. That's how this works. Now, by pouring water into this beaker here, I'm going to dilute the copper plus 2. Its molarity is going to decrease. So the stress is, I'm going to, and I love to write this, here's the stress, here's the response. The stress is, okay, the copper plus 2 concentration is going to decrease. Okay? So I'm going to decrease that concentration. There's going to be less copper plus 2s per volume. And so the response by the reaction is to increase copper plus 2. You can think of it like that. And how does the reaction, the response, this is what we do as humans, the response is what the reaction does to regain its balance, so to speak. It's an analogy. What it's really doing is working toward equilibrium the best way that it can. So how does the reaction respond here? Well, if I take away copper plus 2, it's really hard for the forward reaction to go. And therefore, the reverse reaction can have a chance to pick up some momentum. And if the reverse reaction is picking up momentum, it puts a limit on the forward, and I should have a lower voltage. A better way to understand this, I think, is the idea that I have a reaction. Here is the depth of a reaction at equilibrium. Let's say I'm right here, and I'm going forward a little bit. This point is 100% reactants. Here is 100% products. If I dilute my reactants, I'm going to move this line a little lower. And if you see now, I only have a little ways to go toward equilibrium. When I was farther away from equilibrium, I had more spontaneity. The farther you are from equilibrium, either in forward or reverse, the more spontaneous you are. So now, by dropping the concentration, I'm not going to be as spontaneous in the forward. So stop talking about it. Let's see if I can drop the voltage. I may have to add a lot of water here. So let's do that. All right, so I'm going to add some water. 0.72 is my voltage. And let's see if I can add some water and make this happen. and it was 0.72, and you can see that now I'm 0.71. It's not a huge change, but I'm definitely on the way here. All right, maybe give me another 1/10 of a volt to make me feel good about myself. There we go. All right, so 0.70. It's not a huge change, but it did drop by me diluting the what? Okay, by diluting the reactants, okay, I put a limit a little bit on the forward and I'm less spontaneous. Okay, so now what I'm going to do is take out the salt bridge. This is going to go to 0, okay, because now I have no way to maintain electrical neutrality. And what I'm going to do is I'm going to just take some of this out because now I want to add some back in. So it's all about the copper +2 today. All right, so I'm just pouring some out, okay, so that I can have room to add more. Okay, so in any case, resetting this back up. Here's my copper into the copper chloride. It's a little less, okay, it's a little less concentrated as it was. I definitely diluted it. I'm going to put back in my tubing here for my salt bridge that has the sodium chloride as the salt, and I've got my 0.70. It's not about the volume, it's about, okay, the molarity. Okay, all right, and that may change a little bit based upon how ions are flowing. All right, any case, so the next step here is to do the opposite, okay? I lowered copper +2, the reaction shifted to make more of it, and it went in the reverse a little more, so it impeded the forward. Let's bring back copper +2. Let's bring back my chart again, okay? Now, I'm going to do the opposite. Stress is I'm going to increase the copper +2 solution, and I can use brackets here, all right, for concentration for molarity. What's the response? To lower it, okay, to regain its balance. Okay, and how would the reaction lower the extra copper +2? Remember, the equilibrium position is based upon what's allowable at that certain conditions. So if I increase the copper +2, the reaction is going to lower it and shift to the right. Ooh, we're going to make the forward more spontaneous. Okay, now let's do that. The solution I'm using is darker than what I'm starting with to show you that I'm dealing with a more concentrated copper +2 solution. So let's just stop talking about it. I'm going to add more of a reactant. The reaction is going to shift to get rid of those extra reactants, right? I'm going to move it farther away from equilibrium, and it's going to be more spontaneous in the forward. We should get a higher voltage here. Let's see if I can do that. And success. All right, success. And again, using Le Chatelier's principle, I can drive a forward or drive a reverse. What's nice about redox reaction is that we can measure the voltage, which tells us something about the spontaneous or the spontaneity of the reaction. So now we have a shift forward, okay? And there's a great example of increasing the reactants and the reaction shifting in a way to lower the reactants. So we made a more spontaneous process in the forward, which is reflected in the increase in the voltage.